So
Yeah.
welcome, Gajendra. Gajendra is an assistant professor and lecturer at the Goethe Institute of Technology. We're excited to see your talk. You can start sharing your screen whenever you want.
Yeah, sure.
And as we can see, his talk will be on computation techniques for encrypted data using Python.
Hello, everyone. My name is Gajendra Deshpande, and I'm working as assistant professor in KLS Goethe Institute of Technology. So I'm very much excited to speak at BuzzConf. So I'll be speaking on computation techniques for encrypted data using Python. So these are the contents which we are going to briefly discuss today. So introduction to homomorphic encryption, properties of homomorphic encryption, summary of homomorphic properties, the example, experiment with RSA algorithm, results, machine learning and homomorphic encryption, and finally the conclusion. Now let's first discuss what is meant by homomorphic encryption. Let's discuss it with an example. Now imagine taking all of your credit card statements and locking them into a safe to which you have the only key. So your statements are now protected from the prying eyes. So this is what encryption does. But what if you wanted to analyze your expenditure on groceries in the last 12 months? So first you would have to unlock the safe and retrieve the statements. So now the documents are out in the open and they can be read by anyone. So this is what decryption does. But the difference with the homomorphic encryption is that you can create your report without taking the documents out of the safe. Now, when we say homomorphic encryption, there are basically two types or two basic properties. One is additive homomorphic encryption and second one is multiplicative property. So in additive homomorphic, what happens is you have two plain text PT1 and PT2. You're going to add them and you're going to encrypt them. Then it is equivalent to the encryption of individual plain text sum. Now there are some identities with respect to additive homomorphic encryption. So that is the product of two ciphertexts will decrypt to the sum of their corresponding plain texts. So you can see here we have two plain texts M1 and M2. So both are encrypted individually and multiplied. And when you decrypt it, it will be equivalent to the sum of plain text M1 and M2. So similarly, there are few more identities. The next is multiplicative homomorphic encryption. So multiplicative homomorphic encryption, it is multiplicative if you have two plain texts and you're going to multiply both the plain text and encrypt them. So its result will be equivalent to the encryption of multiplication of individual plain text. So again, there are some identities are here. So you have CT1 and CT2 as the ciphertext. So it is equivalent to the plain text, that is M1 and M2. So we'll see with an example in the later slide. Now when we say the homomorphic properties, there are RSA, failure, L-GAML, elliptic curve cryptography and so on. There are many cryptographic algorithms. So some cryptographic algorithms have additive property and some cryptographic algorithms have multiplicative property. So when these cryptographic algorithms have only one or few properties, then it is known as partial homomorphic encryption. But there are some cryptographic algorithms, some crypto systems such as Gajendra crypto system, which can perform arbitrary computations on the ciphertext. So they are known as FHEs, that is fully homomorphic encryption techniques. Now let's consider this example. So in this example, you can consider there are two plain text P1 and P2. So P1 has the value 5, P2 has the value 10. So when you encrypt both, you will get the corresponding ciphertext. That is, the ciphertext of 5 is 50 and the ciphertext of 10 is 100. And when you add the ciphertext, you will get 150. When you multiply the ciphertext, you will get 5000. But now when you decrypt the result, you will get result of addition as 15 and result of multiplication as 50. Now you can see here this D result 1 is same as P1 plus P2 and D result 2 is same as P1 into P2. Now what we have done in our experiment is there is a RSA algorithm. So this is the RSA algorithm which takes two large prime numbers and computes the system modulus. So n is equal to p into q. So there are some operations in RSA algorithm which are basically multiplication operations. You can see here in this algorithm we have highlighted two lines in red color. So what we have done here is we have optimized these two lines. So we have replaced this normal multiplication operation with more sophisticated multiplication operations, and we have got some results which are promising and which can be implemented on the low resource devices like Raspberry Pi or Arduino or some other devices. So in RSA algorithm, this is how message is encrypted. So to encrypt a message, the sender obtains the public key of recipient. So PU is equal to E comma N and computes the ciphertext M raised to E mod N. So similarly, to decrypt the ciphertext C, the owner uses the private key. So that is PR is equal to D comma N. So and computes M is equal to C raised to D mod N. And you can see here, I have already told you that in one of the slides that we have replaced the standard multiplication that is M P star Q with some sophisticated multiplication algorithms. So the standard method is the grade school method, and the sophisticated methods are the Karlsruhe and fast Fourier transform methods. And you can see the time complexity of all three methods, and you can see here that fast Fourier transform technique is performing better. Now these algorithms will perform better when the number of digits in the number increases. So for the numbers which are having less number of digits, your grade school method may perform better, but for numbers which are having thousands of digits in a number, in that case Karlsruhe and fast Fourier transform will give you better results. So what we had done is the multiplication algorithms were implemented in two steps. So the multiplication algorithms in RSA algorithm were replaced by Karlsruhe and FFT methods, one after the another, and multiplication operations were performed on encrypted numbers by Karlsruhe and FFT methods. Now this was the Python code output which we had written, and you can see here there is a small number, two random numbers were generated, 22 and 87, and when we had encrypted, it had generated the two encrypted numbers. Then when you decrypt the encrypted numbers, we are getting the same result. Now you can also see here the product of two encrypted lists. So that's nothing but we have multiplied the encrypted value of 22 and 87. Now when we decrypt this value, we are getting the value as 1914. So it is the same as the operation on plain text. So that is when you multiply 22 and 87, you will get 1914. Now these are the results which we had got on high resource devices like laptop with standard i3 or i5 processors. And you can see here the first one is the graph which shows multiplication operation in RSA algorithm with the standard methods. And here on the right hand side you can see the multiplication operation on encrypted text. And you can see here the grade school method in both the cases is taking more time, whereas the Karasuba and FFT, they are almost taking equal time. But when you compare the result, Karasuba is giving you the more stable results. So same thing is happening with the low resource device. So here it is tested on Raspberry Pi. So compared to a laptop, of course, it will take more time. But again, if you see here, the results with respect to Karsuba method are more stable. Then next, you can also use homomorphic encryption on machine learning algorithms. That is, whenever you are dealing with machine learning algorithms, you have a plain text, you have plain, you have numbers which are readable. So what you can do is you can encrypt them and train your machine learning model on the encrypted data. So when you decrypt the results, it is equivalent to the results of the plain text. So in this way, you can preserve your machine learning model. So your machine learning algorithm will not come to know about what is the actual data. So the process is you have to first perform the pre-processing. So in that case, what you need to do is you need to map the numbers in the dataset to the random numbers. The next, encrypt the dataset using cryptographic algorithms such as RSA, Payer, or any other crypto system. Then perform the computations on encrypted data. Then decrypt the results. Then finally, the post-processing may be required. That is rounding up or rounding down the value or remap the numbers to the original numbers. Now for that, what we had done is we had used the PyBrain library of Python. So this is the ready-made example available in PyBrain library. So we have changed the input data set here and applied all the steps which we had discussed in the previous slide. And you can see here our values were encoded differently here. So instead of 0 and 1, we had mapped them to 19 and okay. So we had mapped them to 193 and 39. So 0 is mapped to 193 and 1 is mapped to 39. So here we are basically performing the XOR operation. We are training the model to learn about XOR operation. So we are not training it on plain text, that is 0 and 1. Instead, we are training it on some encrypted values. Okay, so you can see here, so it is giving the results correctly. So what you can do now next is you can just remap it. That is, wherever 193 is there, you can just put 0, and whenever 39 is there, you can just put 1. So your machine learning model has successfully learned how to train values which are encrypted. So conclusion is that homomorphic encryption enables computation on untrusted resource. So the computation time over ciphertext can be reduced by using Karsuba or FFT techniques. So training and testing a machine learning model may involve additional steps such as pre-processing and post-processing, and results into additional computational complexity. So what we have done here is we have done experiment only on cryptographic algorithms which are having partial homomorphic encryption properties, but more study is also required with respect to the use of fully homomorphic encryption techniques such as Gantry's or some other more advanced techniques. So there we need to try to reduce the computational complexity. That's because the time complexity there is 10 times more the regular multiplication operations. Yeah, thank you for giving me an opportunity to present my talk at BuzzConf. If there are any questions, I can take. Yeah.
Thank you very much. It's 3 a.m. Where you are, right?
Yeah.
So it's very late. We appreciate that you stayed up so late to give this talk to us. And I wanted to ask about further reading material you can recommend to our listeners and viewers.
Yeah, they can search for research articles with respect to fully homomorphic encryption. That is most there more research is going on, and they can also search for privacy preserving machine learning algorithms.
Okay, and where have you seen these techniques applied? Is there any example that you find particularly interesting in the application of these techniques?
I have not yet seen any applications particularly, but it is mostly useful if you assume that your device is compromised and I want to use the computational capability of your device. So in that case, I can't expose the data in plain text to your device. So in that case, I can send the encrypted data to your device and it can compute. So cloud computing also has some applications with respect to homomorphic encryption.